everyone, and welcome to the third webinar in the Data Science webinar series. Today's topic is Prepping for Predictive, How to Get Your Data Ready for Advanced Analytics with Dr. J. Kyle Roberts. A few notes before we get started. This webinar is being recorded and the recording will be emailed out to you in the next few days. We will also be opening up this webinar for questions at the end, but feel free to go ahead and submit your questions in the Q&A panel found at the bottom of your Zoom window as we go along. A few introductions. My name is Rachel Mason. I'm the marketing specialist here at Technion Data Solutions, helping out with the Data Science webinar series. Be sure to check out our other series with topics in data pipeline, visual analytics, and data strategy, and register for those upcoming webinars because we have some exciting content coming up. And at this time, I'm going to go ahead and turn it over to Technion's data scientist, Dr. J. Kyle Roberts.
All right, thanks, Rachel. Well, just wanted to, in a brief introduction, just introduce myself. So I've been with Technion for just over 2 years now, and am a data scientist here. So I've held professorial positions at SMU, Baylor College of Medicine, and University of North Texas. And a lot of my experience and background is in R. And so I used to teach graduate level statistics courses. And so one of the things that often came up is, boy, once we have data that's really nice and neat, it's easy to analyze. But then as students started getting out in the real world, they started to recognize that, boy, data is never nice and neat when it comes in. And the examples that I always used in class were cleaned, if you will. And so it's a mild level of frustration, but that's okay. It's part of being a grad student. And so it's to have a little bit of frustration there. But one of the things we'd often talk about is, what is the process that we go through before we actually begin analytics? And for me, I bet 80% of my time is spent getting data ready. And then 20% is actually running through models and checking models and actually putting it into production and things like that. And so this first part is even though we're seeing that in the news that data science is being called the new sexy. The not sexy part about data science is data cleaning, data wrangling, putting things together, making sure they work well, and many things like that. So what I wanted to do is just kind of give you an overview today of some of the things that I've seen across time, and in looking at that, maybe give you a couple of ideas for as you're starting to prep data for your analytics. What are some common pitfalls? What are some of the things that you can look to? What are some of the changes that you can make? How can you potentially make improvements on improving that pipeline of taking raw data and then pushing it out into production? And so, having said that, I love this quote from Doug Laney. And if you haven't read this book, Infonomics, it's a great read, definitely worth spending time with. But he said, "Why hasn't our organization been treating information as an asset all along? And how the heck can we hope to thrive, let alone survive, in an increasingly digital world without doing so?" I think what Laney is really pointing at here is that as we're starting to move to a much more digital age, especially I think this has been vaulted forward with COVID and all the stuff going on with COVID. One of the things that we need to look at is how are we treating our data? What are we doing with it? How well is it being preserved? How well is it being pushed across to our analytic platforms? And so the importance of actually spending time ahead of time, making sure the data coming across not only is right, but is right for the type of analytics that we want to do. And I'll be talking about this here in a little bit. The type of analytics that we want to do really is informing just as much as the original data. And so we're needing to make decisions about how we're capturing data because we know how we want to use it when we go into our analytic phase or the predictive phase. And so that's going to have great ramifications for how it's stored, how we then extract it and what we do to it after it's extracted. And so having said that, we are going to cover a lot of these topics. And so this is really the idea of what we're going to do today. We're going to look at, what should the data structure of the data look like when it comes across. We're going to talk about data cleaning, and we're going to spend a whole bunch of time there. because again, clean data is not useful data to us. We'll talk a little bit about feature engineering, and then I'm going to say a note at the end about data enrichment. So I kind of have some opinions about that. That's really what we're going to try to cover today. So if you know me well, or if you've been to some of these seminars before, you know, I always like to talk about the data analysis lifecycle. And the very first thing being, before you begin analysis, before you start conducting data, before you start, placing models in there, the very first thing you really need to do is you need to define your project objectives. This is the whole idea that you're asking good questions before, because lots of times I think, and I've had this happen more than a few times with consulting, and then even in my academic career before this, that someone will literally drop off a data set and say, hey, can you analyze this? And so I'll start to look and just to see, all right, at the data, and I'm going, okay, I can analyze this. However, I'm not even going to be able to tell you too much about what's going on with your data, because we put the data before the question, and the question always needs to come before the data, because as you're starting out, it may be that the type of questions you want to ask just don't exist in your data. And I always love that too. That's when people, drop off the all of the data and say, hey, can you analyze this? This is like people dumping a bunch of metal into my living room and saying, hey, can you make a car out of this? Maybe. So maybe not though. But that's always the problem, is when we receive that data. And so starting at the beginning is really the important part to, all right, what are my questions? And then do I need to start from day one collecting the type of data based on the type of question that I have. And so I love to this quote, your data is only as good as the questions you ask, but the reciprocal of that is true too. And that's what we're talking about today. Your answers are only as good as your data. So, so you have to ask good questions and have data to support that. But then even if you have data, you structure your data around the questions you have, depending on how you put those questions that data together, and how you captured it, and what level of granularity you may or may not be able to answer the question. So that second stage in the life cycle, that's where we're spending today. You're exploring your data, you're getting it ready for analytics, and then we'll carry on down through the rest of the data analysis life cycle again. So today we kind of talked last month about this defining project objectives. Today is really about exploring data. And then, then after that, we begin modeling, interpreting, refining, and then we push it out into production. Okay, so let's start with this. How do you need to structure your data if it's going to be analyzed? So the first is you need what we're going to call completely filled data. And the reason that this is important is because a lot of times when people send me over, let's say, a CSV file or even an Excel file to look at, there's going to be like just open spaces for columns, and they really like maybe the structure of that Excel has some auto table properties that they look real pretty when you're viewing them, but when you push them into analytics, they're not helpful at all. And so when I say completely filled, what we're meaning is we want one row per observation in our data set. So let's look at two examples here. So on the left, if you're looking at this, you'll see really what we have in this square right here, that's our actual data. And then over to the right here, we have some derived values. So, we have the min and the max, a median, there's an average, and then those totals. And then down below, we have totals also, okay? The stuff outside of this square here is not useful, meaning that the stuff outside of it, so in this kind of this almost backwards L shape, the stuff out here, this is stuff I would actually produce inside of my analytics anyway. And so again, this happens a lot, that I get a data set that looks like this, and I immediately know, okay, I don't want any of these columns, these last 5 columns, and I don't want these bottom 5 rows, because the data actually exists that I need to analyze in here. And so this will happen a lot, or someone won't realize it, that maybe there will be another table way over here to the side that is maybe off screen. They'll forget about that, and so they'll send me this data set, and I'll try to read it in, and now I've got all these weird things. And so we want to think of one row per observation. and at the most granular level that we can get it. And so again, so Betty score, these first 4 lines here, for computer software services and devices. I really don't want that total in there also. I want to use that later. I'll derive that later, so we don't want that. So a type of data set that comes across like this versus this one on this right. So this is really simple data set on the right. Again, the column names or the variable names are in the first row. Each row represents one observation. And then this is even, this is quarter data. And so if you see like Williams appears there twice, so in quarter 2, they had 10,644, but then Williams is down here in quarter 1. So it's a little bit odd, a little bit truncated, but it's still one observation per quarter. That's the area that they're looking at. So again, these ones over on the left, really pretty. These ones on the right, really useful when we're starting to get ready to do analytics. And so as many of you probably with COVID have been, especially with small kids, you have been spending time watching shows that necessarily you didn't want to watch. So in the sense of Sesame Street, all right, here's bad, here's good. All right, so that's we like data sets that look like the one on the right. We don't like data sets that look like the one on the left. That's not actually a data set, that's a report on the left there. So that's not something we would want to consider, okay? If we're pulling from CSV or Excel files, okay? All right, so knowing that, again, more on this, how do you need to structure the data? As a general rule of thumb, what you want to do and what you need to do is use the most granular level of analysis you can obtain. So if you have data, let's say data about suppose we're working on the stock market and we're trying to predict stock price. But we only have a stock price that's coming across let's say once a month. Okay, that's really not helpful to us. It's just not at all helpful to us because there's lots of volatility within the month. That's something we're not capturing there. Even if we did weekly or even daily stock prices, that's not great, especially when we're looking at, let's say, penny stocks that have a lot of volatility within a day. They may move up or down 10% within a day, but they all end at about the same level. Well, if you're not capturing that level of granularity, then you're going to be a little bit in trouble. Okay, and here's the reason that this is important. It's very easy to go from, let's say I'm grabbing stock market prices on a microsecond level, every microsecond or something like that, or every 100 microseconds or whatever it is. If I'm capturing at that level, I can easily aggregate up to looking at, okay, let's just look at it every 5 minutes. What's the stock price every 5 minutes? And we may want to do that because the algorithm that we're using for our analysis, it's going to really bog down if we're going to analyze at the microsecond level. So it's easy to kind of generalize and go, okay, actually, let's just capture every 100 microseconds or every 20 seconds or every minute or something like that. That's easy to pull out, really easy to pull out. But it's not when you're the reverse, when you have day level, but you really need to go down to the hour level or the minute level. You just can't do that. So we're always wanting to store our data the most granular way that we can. And again, too, with newer platforms such as like Snowflake that don't charge for storage, this is really not a problem anymore. If you're storing in the cloud, and you're using a package like Snowflake or using a service like Snowflake, they don't charge for how much data you have. It's just for processing time or loading time. And so now we can store it at the the smallest level we need in order to be able to use it. This is really, really important because again, a lot of times I get handed a data set and I go, yeah, I just can't tell you that. You've been capturing it every quarter and you want to know what's going to happen month to month in time series, and you didn't capture it that way. And so a lot of gnashing of teeth and being frustrated. Anyway, so we get the most granular level we can, because this prediction maximizes on variance. And so let me see if I can explain why this is true. There's something in classical test theory called the true score model. And what this is the O is represented by observed score, and that equals someone's true score plus error. And what this means is we're going to talk a little bit about people for a second. I can't know what your true score. So let's say suppose I'm trying to measure your IQ. Like I can't know exactly what your IQ is, but different IQ instruments are better at getting to what your actual IQ is than other instruments. So the ones that are, or even personality assessments. I'm sure you've all taken the ones online that say something like, at the end they say, "Hey, you're a golden retriever," or "Hey, you're a badger," or those type of things. So they're horrible. They're absolutely terrible. I mean, they're fun to take, but they're terrible. They're really not accurate at all. So in those cases, they're trying to get at what your true score is or true attitude based on what they're observing. But there's some error in there. And so I think the problem is that typically we assume that this is what it looks like. Okay, I observed your score and it's about 90% accurate with your true score, and then there's about 10% error. Okay, when in truth, a true score model really looks like this. 40. I observed something, and about 40% of it's really due to you, and about 60% of it is due to some error. So consider, for example, children that we're testing. Let's say on like the Stanford test, that most schools give. There's so many things that could go into why a child scored the way they did that day. They got into a fight with their parents on the way to school. They didn't have lunch that day. They're going through, a really troubling time in their home. They just broke up with a boyfriend or girlfriend. All of these factors that have nothing to do with what your actual score is could be influencing why we observed the value that we did. So when we don't use data at the most granular level of analysis, what we do is we actually inflate the amount of error in our model because we maximize on the fact that people are really, really different from each other, or scores are really different. So again, if we're trying to predict a really, really stable stock price, meaning one that hasn't changed for like 10 years, that stayed right at the same value, then it doesn't matter how many variables we include in our analysis. It's not going to help us predict what changes we see in that stock because we haven't seen many changes. But stocks that are really, really volatile, the more data that we can put into our model to predict that volatility, the better. And so we have more volatility when we have a smaller level of analysis, meaning more granular, getting down to that second level. Okay, or the minute level, or even the hour level. But when we start looking at the end of the day score versus the end of month score, we're not going to maximize on that. So we need to get at the smallest level that we can. Okay. Hopefully, I've spent 10 minutes just trying to make that one point. So hopefully that horse is dead. We've beaten that horse and we don't need to anymore. Okay. All right, so again, on how do you need to structure your data, you also don't want to steal variance from your variables. And so by that, I mean this. So let's suppose we have a variable that's this variable on the left that's score, and we have some scores in there. And then instead of actually saving the people's scores, we actually put them into quartiles. Okay, so a certain person with an 8 is the 4th quartile, and 5th is the 1st quartile. Okay, what we've done is we've stolen variance, so there's a lot of variability in this score, right? And then we've taken that out into this quartile. Now, actually, this one is not the best of examples because you really only have 4 scores over here and 4 scores over here, but you kind of get the idea. This is even more pronounced in something when we do something like this. When we take scores on an exam, and then we actually put that in a grade on a 4-point rating scale. And here's the problem. The person who made a 90 and the person who made 100, we're going to put them in the same group, okay? But there's actually quite a bit of difference between those people. This first person made a perfect score, and this one, got 9 out of 10 of the questions right. But we're going to now group them together, okay? Now, do you see how we've just stolen variability from this? Okay, and then an 80 is a 3. Okay, a 65 would be a 1.0. Again, 83. 26 is 0. Even though anything below 60 is actually 0, it doesn't matter. That scale is now from 0 to 59.4. They all get a 0.0. And then here's the crazy part too. This 79, the difference between a 79 and an 80 is only 1 point or 1 percentage point. But the difference between a 79 and 80 on this scale is a whole bunch. I mean, that's almost 25% of your scale, okay? Or really 20% if you think of it, we're counting a 0 also, okay? 20% of your scale. That's a big jump. Now in the score, that's only a 1-point jump, but here that's a huge jump, okay? in that grade. So we don't want to steal variance from our variables. So we always want to store it in the, the most granular level. We don't want to steal that variance by putting them into groups afterwards and then starting to analyze those groups. Okay, or even using that as an independent variable. Okay, so a quick word about time series and how you store your data when it's in time series. Okay, most of the time when you store data in a warehouse across time series, you're going to have something like this, where you're going to have what we call wide data. This is totally fine for storing it, but I wanted to point out that you're not going to analyze it in this format. So we have, January is one column, February is one column, and then we just had new columns that we're adding to our data set based on, whatever level. If this is, stock prices, then each stock is at each time point. In order to analyze it, we're going to have to store it in what's called a long format, okay, where we're actually pivoting that down. If you're using Alteryx or a program like that, and you'll use the crosstab and the transpose functions in order to do this. If you're in R, then you'll just use a function called with this lowercase letter t. So we're going to transpose this data to manage it the way we want. But suffice it to say, we always want to store data the way that we envision using it. However, time series is a little bit different because we're always going to store it wide and analyze it long. Okay, and so I just wanted to pick that in there because when we're talking about how do we store it and where do we keep it and things like that, at the granular level, this is a little bit different when we're going to look at in time series because we'll eventually pivot that down. Okay. All right. So what does your dependent variable look like? That's kind of the next question we're going to ask ourselves. And so really your structure of your dependent variable can be three ways. It really can be four, but the fourth is what we call ordinal data. But analyzing ordinal data is really hard, so I'm not going to talk about it here. But your dependent variable really needs to be one of three ways. It needs to be either nominal, which in that type you're going to have, like, let's say categorical data, or ethnicity. So in this case, we're, categorical data like they belong in group 1 or group 2 or group 3, and you're trying to predict which group they belong to. Okay. It can be dichotomous data. So meaning, that's yes, no, or 1 or 0, or died or did not die, so we're looking at mortality there. Or we can look at, or it has some trait or doesn't have some trait. Okay. And then we can look at what's called interval or ratio scale. This is always dependent variable needs to fall in one of these three, with the exception of we can do ordinal, but we don't like to do that. It's really difficult to do. So and most statisticians are going to shy away from ordinal. So this is interval ratios data on a true continuous scale, meaning we have equal appearing intervals, meaning the space between 0 and 1 is the same as the space between 1 and 2. For example, a GPA scale, that's not the case because the amount of space between 0 and 1 is different between the space between 1 and 2, and 2 and 3 and 3 and 4. 1 and 2 and 2 and 3 and 3 and 4, that's all the same space, but 0 to 1 is a bigger jump on that. Okay. And so we might look at, let's say, heartbeats per minute, and then what we're thinking about is that how are we going to analyze later? When we go to our analysis, which again isn't the point of today, the nominal and dichotomous data can be analyzed with classification systems, and then you can also analyze dichotomous with regression systems, like for logistic regression. But then this interval ratio data can only be analyzed through regression. We can't do it through classifications unless we steal the variance, and we don't want to do that, right? We don't want to do that. Okay, all right. So what about data cleaning? So once we've got our data, we're pulling it in, and so we're asking the question of what do we need to do with it now? Like, how are we going to clean it? How are we going to get it ready for prepping it for the prediction? Okay, so the first thing we may want to do, now we may not want to do it, but we may want to do it, is aggregating classifications. So what do I mean by this? Well, let's suppose you are looking at ethnicity, but when you are looking at ethnicity, let's say you're looking in the United States at ethnicity of students in classrooms, and one of your ethnicities is Native American. Okay, that is a really, really, really small percentage of all of the students that you're going to have in your analysis. And then you may also have, let's say for some reason you have Asian Pacific Islanders, so not just Asian, but just Asian Pacific Islander. And you say that's a really small amount too. And so there may be a case where you say, okay, I've got like 4 ethnicities, but then I've got these other 5 that are really small, and I want to combine them. And the reason you want to do that is because it's going to violate in some of your assumptions when you run your analytics test. So there may be a time that you go, okay, this group is too small, and so I may need to aggregate them. Only have 3 in this one group, so I may even want to leave them out for some reason. But you have to have a good reason, kind of, for thinking about either leaving them out or aggregating them in other classifications. Okay, when it does come to, but so I want to make those decisions before I start the analysis. I'm gonna look at reports from that and go, okay, here's all the classifications that I have. And then also too, sometimes we have a classification variable that has, let's say, 100 different possibilities. And so let's say we're analyzing bank data and we're looking at transactions, and a whole bunch of them are deposits, but we have 20 different deposit codes. And then a whole bunch of them are ACH, but we have 30 different ACH codes. And then a bunch of them are transfers, but we have 12 different transfer codes. We may want to aggregate them all into, okay, here's deposits, here's ACH, here's transfers. So we may want to put all those together. So that's where we do this in kind of this data cleaning stage. And then the second is we'd remove outliers if appropriate. Okay, so if it did make sense to remove outlier. We always want to ask the question, why is an outlier there? But we may want to remove that outlier. So in doing so, we typically want to remove outliers after we've determined, hey, here's a good reason for removing that outlier. But one of the things we also may want to do is remove our missing data. And we have 3 categories that we typically think of when data is missing. And 2 of them are kind of okay. One of them is okay. 2 of them, the second is kind of okay. The third is never okay. Okay, we always have to do something with that. So when we have something that's called missing at random, or MAR or MAR, so it's not completely related to the missing data, but related to some other observed variable. So for example, we may be missing IQ scores for some kids, but it's only because they're younger children and they just haven't had an IQ test yet. Okay, it's not because they didn't want to give you their IQ or something like that. It's just because they're young and we haven't given them an IQ test yet. Okay, missing completely at random. So that's usually okay if it's related to some other variable. Then we're usually okay with that. Not awesome, but usually okay. When it's missing completely at random, meaning like we have no idea why it's not there. There's nothing that's causing this to not be there. It's just we just don't have it. So it has nothing to do with the data. That's the one that's okay. Now the missing not at random, this is the one where we're going to have trouble. The missingness is actually related to the variable itself. So let's suppose we're calling people on the phone, and we're asking them to report their salary. In that case, typically wealthy people do not want to report their salary. Okay, so they're very hesitant to give it out to you, especially when you call them on the phone. And so there is a reason why it's not there, and it has something to do with the variable that we're actually reporting on. Okay. So in that case, we've got a problem, and we actually have to go back to, and there's really good questions on whether or not we can actually get this information and whether or not this variable can be included in our analysis. Okay. This missing not at random, that's when we're going to typically stop or kick them out of the analysis, or try to go back and investigate why, and maybe ask the question differently. Okay. So once we've determined, why it's missing, how do we handle that missing data? There's really 2 ways we can go. One is by using what we call deletion techniques. And so there's really 3 ways that we can do deletion. We can do listwise deletion, meaning that let's suppose we have 5 variables, and if a person is missing any one of those 5, then they just get kicked out of the analysis. Okay. We can do pairwise deletions, meaning that a person's observation is removed from the analysis only when it's used in conjunction with another variable. So let's suppose we're looking at, let's say, ethnicity and gender, and then salaries. Then let's suppose we're missing the gender for one person. Well, then we can still analyze the ethnicity with salaries, but when we include gender in the model, that person would be dropped. Okay, just in that case. And then columnar deletion, this happens frequently when you have a variable that has a ton of missingness in it. And so we just generally decide, okay, for everybody, we're going to get rid of all of their scores. Okay. Now, again, deletion, we always like data. right? And so whenever we have data, we typically don't want to delete it if we can still use it. And so there are some techniques that we can do in order to keep that data in there so that we still have, we still have a lot of data, because we want variability, we want lots of people, but we do have to talk about, okay, how are we going to handle it if it is deleted? If it is missing. We don't want to delete it, but sometimes we have to. Sometimes we do. So, but if we're not deleting it, how can we handle what we call imputation techniques? So there's a couple of ways that we can do this, or a few ways. We can do, we can either just take the mean and put it in for that person. We can take the median and put it in for that person, or the mode and put it in for that person. We can impute that into, so everybody who's missing on this variable, we're just going to put the mean of that variable in there, or the median, or the mode. This isn't, oddly enough, even though it seems real simple, it's not often the worst case in the world in order to do mean imputation into someone's scores, okay, as to why they're there, as long as we don't have a ton of missingness. And so if we have a lot of missingness, and then half of our data is a missingness variable, and we put the mean in, it's really not going to help our analysis. And we also have to recognize that's not their actual score in this, so their actual score could have been really different. And so, but doing this will typically not hurt you too much, and will still allow you to leave that person in the analysis, but just for that variable, their score is kind of meaningless, okay? We have something else called hot deck imputation, and that's where you borrow information from your current data. So let's suppose I have 4 variables predicting the 5th, and then somebody is missing, let's say, something on variable number 3, then what I can do is use variables 1, 2, and 4 to predict what they would have scored on 3 if we had known it. So you're basically kind of using your current data to predict what somebody's score would have been, and then using that in your analysis, okay? This is hot deck imputation actually is pretty neat. I actually like it. And so it's kind of hard to run. And so you probably might need some help the first time you do it. It's kind of hard to do, but it is neat. And then we have hot deck, after hot deck, we have cold deck imputation. And that's where, let's suppose you had information from that person on a previous data set, okay? Then you can actually borrow the information from previous data and then push that into the cold deck imputation. That's as good as long as there wasn't massive change from or even a little bit of change from the previous data set to now. So again, if you're wanting to borrow their ethnicity from the previous data set, you're probably going to be okay, no problem at all. But let's suppose you're wanting to borrow their height from the previous data set, and it's been 2 years, and their children, probably a bad idea. Okay. All right. There are a lot more regression-based techniques that are a little bit harder, and so I'm just going to kind of lump all them together. There's, again, if you search for this, it was just a regression-based imputation, even though hot deck is a regression-based, but there are other flavors of this. And then interpolation from time series. Is when let's say you, for some reason, are missing someone's January score, but you have, April through December, and then you have February on through August or something like that. Then interpolation is generally, if you've noticed some sort of trend in that person, then kind of interpolate based on the trends. And it's usually like the average of the 2 closest scores, or average of the 2 closest scores based on some factor of what they did at the same time last year or something like that. You can use those interpolation techniques. Okay, so here's the one caution: it's not your data anymore. When you do handle missing data and you do these imputation techniques, that's not your actual data. And so we do proceed with caution here. And so there is some warning. And the warning is you don't always need to use an imputation technique. Now, why is this important? Let's suppose I'm wanting to do an analytic method that is, let's say it's using some sort of empirical Bayes estimation in it. Well, now I don't need any imputation technique, because the empirical Bayes, what it will do is just, it will take from the information that you have, and it will actually kind of process up, if you will. And so I wouldn't, in a case like that, I wouldn't want to use any imputation technique, because I'm still going to use as much information as I have. And if I don't have information from someone, that's still okay. They can still be included in our analysis. We'll actually push forward on that. Okay. So this comes in with knowing, how do we handle missing data? Also, part of that is knowing how are we going to analyze this data. And that will, again, sometimes really inform you on, okay, you should use this type of imputation, or you should just leave it alone, don't do anything, or you should do listwise deletion, based on not knowing these things. Okay, so having said that, that's a lot of information there, and I understand that. But how you handle that missing data it really does depend on what type of analysis you're going to do afterwards. And there's been a ton written on this, absolutely a ton. All right, then we also do some, after we've done that, okay, we've handled our missing data. We've tried to figure out, we've got it at the right granularity level. We've handled the missingness, and then we want to do some feature engineering or creating new variables. One of the things we can do is something called dummy coding. And here's how this works. And that let's say you have a variable that's school, A, B, C, A, C. If you're doing a regression-based technique, you can't actually include this in an analysis. You have to do something called dummy coding. Now, a lot of your software packages will automatically do this for you, but really what's going on is it's creating synthetic variables where you have a school A variable where everyone who had a score of, is in school A, they get a 1 for this variable, and if they're not in school A, they get a 0. And the same thing for school B and the same thing for school C, okay? So you've got this this variable, and actually there's a lot of math behind why this works, and what you're doing is you're splitting up the variability or the variation, or I'm sorry, the variance that is due to this variable into each of these schools, and so, or each of these other variables in order to be able to use it. So if you are doing regression-based techniques and your software won't do this for you, this is something you're gonna have to create yourself, okay, in order to include in the analysis. So you may have to do some dummy coding. You can even do a version of this that's called planned contrast, where you actually say, you know what, I really just care about doing school A and C versus school B. And so in that case, you would have a variable that is school A and C. And so this person would get a 1, this one a 0, and then these 2 people or these 3 people here would also get a 1. And so that would be school A and C versus school B. Okay, so we can do that for a planned contrast. All right. And then the other thing is looking at interaction effects. Now, there aren't hardly any software packages out there that will actually do this for you just out of the box. And so generally you have to create these interaction effects yourself. I'm going to bring this up. I'm not going to talk about how to do this because it would take more time than we have today in order to talk about that. But that's when you're looking at, let's say, the effect of, I'm looking at gender versus their actual what program someone is in, and so I'm looking at, and so I'm deciding, okay, I'm just going to split these into these 2 genders and then these 3 programs, and what I want to look at is the difference between being in let's say gender 1 and then program 1. That's this dotted line here. So there's that score at the beginning, there's that score for gender 1, there's that score for gender 2, and then same thing for this dotted line. But then we see an interaction effect here, a big interaction effect where school gender 1, and then when we move to in program 3, when we move to gender 2, that really makes a difference, makes a huge difference in our analysis. And so we would call this an interaction effect. And in this case, we might not actually see that there was any differences between the genders or that there was any differences in the programs, but it does matter what gender you are in what program. Okay, so we would need to actually run those ourselves. And this is just synthetic data that I created just to kind of prove the point here. But sometimes it may not matter that you went to a certain school, and it may not matter whether or not you were in athletics, but it does matter if you went to a certain school and were in athletics. Okay, and so that we see those interaction effects. Now, those are variables you're going to have to create on your own, the feature engineering. But again, thinking ahead about that of the, hey, you know what, I got a bunch of variables, and maybe this one doesn't really mean something, and this one doesn't really mean something. But boy, when you put those 2 together, boy, you have a really volatile reaction. So, for example, Mentos in your stomach don't do things. Diet Coke in your stomach don't do anything. But you put Mentos and Diet Coke in your stomach, and boy, it's coming back out your nose. That's the analogy here. Okay, so sometimes that interaction effect is really powerful. Okay. All right, the other thing that you would want to know in feature engineering is working with dates. And so if you have just a date, sometimes it doesn't matter the date, but it does matter, what day of the year it is. So it's 100 days in, or it's 200 days in. Or sometimes it may matter the day of the month, or actually the day of the week. So really, if you're looking at retail sales, whether or not it's a Saturday or Saturday, all you have is actually the physical day. And you need to generate from this, you need to generate a feature that says whether or not it's Saturday or whether or not it's Sunday, because those are the days that at your retail store, you're getting a whole bunch more bunch more sales, or maybe you're getting less sales, or maybe what quarter you're in is important, or what month you're in, or even sometimes what season you're in. Well, if you're selling lawn equipment, the season matters a lot. Okay, winter you're not selling a lot. So again, these are the things that I'm going to want to do ahead of time. I'm going to want to consider, how do we get, what type of dummy coding we want to do? Do we want to do interaction effects? What do I do with the date? How am I going to decide, what matters when I'm looking at date? Well, it depends on, what type of data we're analyzing, and then from there. Okay, so that is a lot of information to process, and a lot of information to go through. And so I want to point you to, this is our website, Take Me On Data Solutions. It's takemeonusa.com. And the reason I want to bring this up to you is because there's lots of opportunity on our website where we're putting up webinars on, hey, or even blogs on, I've got this weird data set and I've analyzed it this way and it made me think about something, so we wrote a blog about this. You can get to this through our website, and start to look at some of the blogs that we're putting up, especially, we're doing a lot around Alteryx and Data Robot and Tableau. We're starting to put a lot of things forward. And then we even have some stuff in there just on statistical theory, like you'll find there's one in there that I wrote about, what are p-values really useful when talking about statistical significance testing. And so do they actually help, or are they a hindrance to us, or would they mean that we possibly are missing something when we run our analytics? Okay. And then finally, you can follow us on Twitter or LinkedIn. So you can link to our, if you like our, connect with us on LinkedIn, we'll give you lots of opportunities for many more webinars like this, and then also blogs that we're creating. Okay. So Rachel, I'm going to turn it back over to you. I don't know if there were any questions that needed to be answered, but that's all I have for now. So Rachel, just turn it back over to you. If I need to answer some things, let me know.
Great, thanks, Kyle. Yep, we're gonna open up the Q&A. So feel free to submit any questions you guys may have. And if we don't have any questions, then we'll be wrapping up this webinar shortly. But just a reminder, this session was recorded today, and the recording will be emailed out to you along with the slide deck within the next few days.
And also, if there are other questions about, hey, I'm doing this type of analysis and I've run into a roadblock, or I need some help here, please don't hesitate to, through the Take Me On website, you can reach out to me and you'll see my email address there. And so shoot me a note, and then don't hesitate to reach out and ask that question. So
definitely.
Yeah.
Okay, well, I'm not seeing any questions. You have some praise in the Q&A, Kyle, for a great session. But like Kyle mentioned, you can reach out to him. I'll also include his email in the follow-up email, so you'll be able to reach out to him through there as well. But thank you so much for tuning in today, and we hope to see you again in another webinar.